Hello, this is Alistair Plotnick with the Physics 2212 Lab 3 for circuits for summer 2024. So first, introduction purpose is to examine the behavior of circuits in parallel and series that contain an ohmic resistor and capacitors, measure the values of potential difference in potential current with these circuits, and predict the behavior of these circuits using a virtual model. So the basic models used here were the node rule, which is I in equals I out, the loop rule for any round trip, dB is 0, Ohm's law, dB equals IR, and properties of a capacitor. So previous results, the total potential difference across a series circuit is 0 due to the round trip rule, and the time-dependent voltage across a discharging capacitor is calculated as 5.988 volts. So the assumptions I made, I used the virtual circuit component, so I am using that this virtual model will correctly model the real circuit components, and my circuits will be in the steady state so that we can apply the node and loop rules. So the procedure for the charge energy conservation in series circuit, I use the online circuit construction kit. You can see the picture to the right. For ammeter, I1 equals I2, which was 0.02A and negative 0.02A when backwards, when it's connected backwards. Replacing I1 ammeter with a voltmeter, the voltage was 3 volts from batteries, and the current on the ammeter was 0A. The voltmeter has a high internal resistance, essentially zero flow charge. So the procedure for the potential difference in the series circuit, the voltmeter was removed from the circuit, and so the circuit was closed with a wire. The measured potential difference between points in diagram using the voltmeter is to the right, you can see in the chart, and the current was 0.02A in a closed loop with I2 as only an ammeter, and then you can see the graph potential versus position around the loop as well as the circuit itself. So the procedure for the current in the parallel circuit, the voltmeter across the 100 ohm resistor is an ammeter that reads 0.02A, and when the voltmeter is replaced with an ammeter in parallel with resistors, the current in both ammeters reads 0.06A. This is because of the node rule. The current in is split at the node because or between the ammeter and the resistor, so some current encounters no resistance. Overall current increases once the junction recombines so that the current out is equal to the current into the miniature loop. And so in calculating the resistances, I calculated the resistance of the resistors, ammeter, and wire based on the experimental values. Ohm's Ohm law, so here rearranging R equals V divided by I. And so the resistance with the 47 ohm resistor was 0.96 volts over 0.02 amps and equals 48 ohms. For the resistance of the 100 ohm resistor is 2.04 volts divided by 0.02 amps and 102 ohms. And resistance on the ammeter was 0, and resistance on the wire was also 0. So for the RC circuits, charging and discharging capacitors, construct an RC circuit with 200 mF, capacitor 9V battery, and 10 to 20 ohm light bulbs. As the capacitor charges, the light dims and ultimately stops glowing when the capacitor is charged. Current decreases to 0, and same for direct connection of light bulb to a capacitor. As the capacitor discharges, the light dims and stops glowing. Current slows to a stop as the capacitor discharges in the reverse direction. So here, the measuring times for discharging the 10 to 20 ohm resistors. For the 10 ohm resistor, the charging time was 8.5 seconds. The discharge time was 9.3. For the 20 resistor, the charging time was 17.1 seconds and discharge 17.9. And for the 20 ohm bulb, it takes about twice as much as it would to charge/discharge than the 10 ohm bulb. And so for the graphing, I set the capacitor to discharging to plot 20 seconds worth of voltage versus time data using the equation CV divided by dV naught equals minus T over RC, where RC is the time constant of a circuit. The slope was negative 0.617, and the RC was 5.988 volts. So what if we were doing this lab in real life and used an actual ammeter instead of an ideal simulated ammeter? What if the difference was different about a real one? The current is measured by a real ammeter would be lower, as a real ammeter contains some resistance, while an ideal one does not. And then if we're doing this in real life and use the battery to charge a real capacitor with no resistor in the circuit, how quickly would the ideal model predict this? The capacitor would take longer to fully charge as every component of the circuit has some resistance because they are not ideal. So our conclusions: the total potential difference across a series circuit is 0, which confirms the loop rule. The time-dependent voltage across a discharging capacitor was 5.988 volts, and the node rule / loop rule were upheld in our interactions with the virtual circuit creation kit.